Hello, welcome to Electronics Education. This is Vincent Chang. In this lecture, we are going to continue our series around the operational amplifier circuits. Non-inverting operational amplifier circuit. Inverting versus non-inverting operational amplifier circuit. On the left-hand side, it's the inverting amplifier. The inverting amplifier, the input signal Vi is going into the inverting terminal of the op-amp, and the feedback is connected between the output terminal and the inverting input. And again, the closed loop gain of the inverting amplifier is negative, and its magnitude is determined by the two external resistors. Now, on the right-hand side, it's the non-inverting. Why? The input signal Vi is going into the non-inverting terminal of the op-amp, but still, it's the negative feedback. The feedback is still connected between the negative input, the inverting input, and the output. So this circuit is called non-inverting amplifier. So this lecture's focus is on the on the right-hand side of this slide, the non-inverting amplifier. And another interesting phenomenon that you can pay attention to is the red Vi and the blue ground. You see, they are interchange to each other. If you flip the red Vi and blue ground, it will become the right-hand side circuit, right? And if you pay attention to, just look at the right-hand side circuit and you flip the red Vi and the blue ground, and you will go back to the inverting circuit on the left-hand side. That's the interesting thing you can pay attention to, the relationship between these two circuits. So now let's focus on the non-inverting amplifier. Again, the Vi go into the non-inverting terminal. Still is the negative feedback connected between the inverting terminal and the output terminal. So first is the nature of the virtual short circuit. If the op-amp is ideal, if the open loop gain A is infinite, in the ideal case, ideal op-amp, the open loop gain A is infinite. Remember the two criteria when the virtual short circuit is true. What are the two criteria? Number one, it's the negative feedback. It's in the closed loop configuration. And number two, it's in the ideal case. All right? So number one, the first criteria is the op-amp is connected in the negative feedback, the closed loop configuration. And then number two, the open loop gain A of the op-amp is infinite. So in these two conditions, the virtual short circuit is true. The two input terminal of the op-amp, the voltage of the two input terminals should be the same. Therefore, the input terminal, the inverting terminal of the op-amp will be equal to the external input signal Vi. Closed loop analysis. You can get this current, right? So Vi divided by the R1. And then there's no current going into the op-amp. So the current flowing through the R2 will be equal to the R1. So therefore, the output voltage VO will be the Vi, the inverting input terminal voltage, plus, right, the potential increase. When you against the current, it's the potential increase, voltage increase. What? The drop. The current times the R2. The current Vi over R1 times R2. The closed loop gain G will be equal to 1 plus the R2 over R1. There's another way to look at this. When the two resistors, the current going through the two resistors are the same, then the voltage relationship will be based on the relationship of the resistors, right? So it's the voltage divider rule. So if you just look at this based on the voltage divider rule, then you can get the same result. You can get the same. Do you understand what I just said? The VI, the current are the same, right? So what's the VI? You can just put this down. So VI will be equal to VO times what? Times what? Times the ratio. What ratio? What ratio? The denominator R1 plus R2. What's the numerator? The R1, right? So the ratio, the factor, will be, again, the VI equals VO. VI, just put it down. Just write down this. VI equals VO times what? A factor. The R1 divided by R1 plus R2. So you can get this result. Same result. Input resistance. The resistance seen by the external input voltage source. The resistance between the output non-inverting input and the ground. So what's the resistance between the non-inverting input and the ground? The resistance seen by the external input source. What's the current? The current is 0, right? There's no current. So therefore, the input resistance of the non-inverting amplifier is infinite. It's infinite. So the input resistance of this non-inverting amplifier is infinite. Takeaway. So two takeaways. Number one, the gain, the closed loop gain, and the input resistance of this non-inverting amplifier. So what is the closed loop gain? What is the closed loop gain? 1 plus what? The ratio. The R2 over R1. So once you get the virtual short relations, the voltage of the inverting terminal is very easy to get the voltage of the output. And then what's the input resistance of this non-inverting amplifier? Infinite. So do you have to consider any trade-off between the input resistance and the closed loop gain as we did in the previous inverting amplifier? No, you don't have to consider this kind of trade-off. So high resistance, high input resistance, and high closed loop gain, you can have the high input resistance and the high closed loop gain. When you pursue a high gain, high voltage gain, you don't have to sacrifice the input resistance. That's the advantage of this amplifier compared to the inverting counterpart. All right? So this is the first takeaway. The second takeaway is, let's just look at this circuit again, the non-inverting amplifier. On the right is the non-inverting. The VI going into the non-inverting terminal of the op-amp. Now this is the closed loop gain G, 1 plus R2 over R1. What about the inverting amplifier? It's negative R2 over R1. In the circuit theory, there's the theory called complementary transformation. For a linear network, if you interchange the VI and the ground, if you flipped the VI and the ground, let me repeat this, all right? Look at the left. If you flipped the red VI and the blue ground, the ground goes to the VI, then VI goes to the ground, then it becomes the right-hand side circuit, right? And look at the right. If you flipped the VI and the blue ground, then what? If you flipped, then you go back to the inverting counterpart. So in the network, for a linear network, if the two circuits you can flip the VI and the ground, then the relationship between the gain of these two circuits, they are complement to each other. In other words, the gain, the sum of these two gain will be equal to 1. The sum of these two gain will be equal to 1. So this is an interesting circuit theorem called complementary transformation. Complementary transformation. In other words, if you do a complementary transformation for the inverting, it will go to the non-inverting. If you do a complementary transformation to the non-inverting, it will go back to the inverting. And the relationship between these two circuits is very interesting, right? The sum of these two gain will be equal to 1. This is the takeaway. So this is the end of the lecture, non-inverting operational amplifier circuit. I hope you received something from this lecture. Thanks for watching.